So the first thing that you'd want to tell me is, what does that 0 represent? So in function notation, we usually have f of, hey, the screen's still frozen, hot dog. We have f of what? F of x. So what does that 0 represent again? The x value. So I need to go to an x value of 0 and find out what my y value is. So f of 0 is 4. What is f of 3 pi over 2? So I need to go and find an x value that's of 3 pi over 2. And what do I get out for the y value, my output? It's a 0. And then 3 pi, I'm looking for an x value of 3 pi. And so I should get out a -4. All right, here we are reviewing domain and range. Domain is related to what? Your x values. With this particular graph, this graph is limited from the x values on this right side to the x values on this left side, and it's contained in between. If you notice, there are closed circles on each of those endpoints, so that would mean that our inequalities would have equal signs. Or if we were writing it in interval notation, we would have the brackets, right? So my domain, what is the lowest x value over here? 0. What's the highest x value over here? 4 pi. So you can write it in those two different notations. Either this is interval notation on the right here, and this is set notation on the left. 0 is less than or equal to x is less than or equal to 4 pi. And then the range, I always go low to high. So what is my lowest y value? -4. What's my highest y value? +4. So here's your two different ways of writing it, either in set notation or in interval notation. Set notation is that that's first, and interval notation is that that's second. Now it asks us to list the intercepts. If you're given a graph, I'm pretty sure that you guys are fairly comfortable with being able to list the intercepts. We're looking for where does it cross the y-axis, and then where does it cross the x-axis. So it's got 4 places that it crosses the x-axis. You would list them out. And it's got 1 place that it touches the y-axis. So it has them listed out here. All right?
Why is the y-axis different than you move that square back?
Yeah.
Why is it on they're just larger? I was like, why is that one small? See how 0 and 4 is smaller than the rest of them? Like
Smaller is because it wasn't written, didn't have to be in a fraction font. So you've got your, they had to enter it in as a fraction font, so it does make it a little bit larger when you have that fraction to have to. How often does the line y is equal to 2 intersect the graph? So y is equal to 2 is this line right here. How often does it intersect the graph? 1, 2, 3, 4 times. For what values of x? Now notice what this one says. For what values of x does the function equal -4? So remember, f of x needs to be replaced with the letter y. So where in x does y equal -4? Pi and 3 pi. Good. Excellent. And for what values of x is my function, is my graph y greater than 0? So what values of x? This is going to be several intervals that we have to write, because the values of x from here to here, it's greater than 0. From here to here, it's greater than 0, but also here, so we might as well go from this x value to this x value, correct? And then from this x value, we're also greater than 0. So let's see how this works. Well, this one stops, so we'd have to stop at that particular x value as well. So it looks to me like the x values of 0 to pi over 2, and then the x values of 3 pi over 2 all the way to 5 pi over 2. You're going to have, oh, good, good. You're going to have to do the union. Now it's asking for, do you notice that we don't have brackets on the 3 pi over 2 to 5 pi over 2? Why do we not put a bracket around those? Because those are on the 0, which is equal to 0, and you only use a capture when you're capturing it and actually touching it. And then from 7 pi 7 pi over 2 to 4 pi is where it oscillates. All right. I don't know that we need to do this, but obtaining information from a function. If you are given a function, f of x is equal to x divided by x plus 1, if I ask you, is the point 1 and 1/2 on the graph of f, would you know what to do? Plug in. And verify that when you simplify down that you would get or wouldn't get. So hopefully you would put a 1 in for x, a 1 in for x, and do the simplification. 1 over 1 plus 1 is 2, and I should not be using that yellow. That's kind of ugly. So my output when I simplify does verify that this point is on the graph. If x is equal to 2, what is f of x? It's asking you to substitute it in and give me a point. I thought we would look at that, but here's what I'm concerned about is, will you be able to show me the work? You should be able to show me the work. Don't just tell me yes. Substitute it in and actually make it work. Now, this particular function looks intense, right? But we're going to put it into our graphing calculator, and we are going to analyze some information. First of all, part of this course is that I teach you how to use the calculator, the graphing calculator. That's part of the course description. I'm not requiring you to have one, but I'm going to at least show it to you on the screen so that you have that exposure. So those of you who have one, get it out. If you don't, go find somebody and at least sit next to somebody and use theirs. So where are we going to put this function in at? Where are we going to put it in? What do we do? What's the first button I'd have to push in order to get this? Y is equal to. And so y is equal to is going to be where we will go first, and then we're going to replace it with all that mess. So I froze mine so I can actually put it in. So 156 squared minus 34.9x plus 1212.57. Plus, do me a favor because you're going to get mad at me if I don't tell you this, and then later on you figure it out. This is a fraction. Somebody asked me yesterday, how do I put a fraction into the calculator? What is a fraction? Yeah, right. But put it in parentheses. Don't just type 20,000 divided by x without putting it in parentheses, because you need to indicate to the calculator that this is one thing. That you don't want it to do all of this and then divide by x. So make sure you put it into the calculator as such. Hit graph. Why does it not show up? Because my window isn't appropriately scaled, right? So since this is the average cost of manufacturing X computers per day, I really don't even need the second and third or the fourth quadrant, do I? Second, third, or fourth quadrant. Because first of all, I'm not going to compute a negative number of X computers, right? And I'm also hoping that my cost won't be a negative value either. That doesn't make realistic sense. So I'm going to go to the window, and I'm going to make my min of X to be a 0. And then I'm going to increase my X max. If I look right here, it says it wants me to determine 50 computers, so I'm going to go a little bit above that, so I'm going to go to 60 computers. This X scale says, how do you want my tick marks to be represented? You can do it by 1s, you can do it by 5s, you can do it by 10s. It doesn't really matter at this point in time. My Y min is going to be a 0, and I don't really even know what my Y max would be. I'm thinking cost-wise, possibly, oh, I don't know. Let's go 1,000 and see what we see. I don't even know. So I got to try something, but I got to have a little bit of knowledge to go after it. So let's see if that works for us. Okay, so I still don't see anything. So what I'm going to do is I'm going to go and calculate a value. Even though it doesn't show me, I'm going to calculate an X value of 30 and see what the cost of 30 calculators is. So did y'all see where the calculate was? Second, calcs in yellow. Eric, is your calculator the same? Does it have the calc in yellow? It doesn't? Okay. It may be under the math function. Right. Right. But at least I was able to get an idea without just guessing around, right? So I tried one of the values that it asked me, and so I've got 1,300, so I'm going to have to go above 1,000. And I'm going to go ahead and type in 60, which is, oops, delete, 60, because that was the highest X value I put in. So I need to go at least to 1,500 on my window. Do you see this number right here in my function? You see this number right here? When X is 0, well, you can't really have X is 0, but this is going to be your smallest value given the smallest value of X. So your 1, 2, 1, 2, your 1,200, 12, 57, that's going to be a good indicator of your window as well. So I'm going to go up to 1,600, and I probably could not go to 1,200 and it still is going to capture it right in between there. Okay. So if you're thinking about cost, do you see how it comes down and reaches a minimum value right here? This is a minimum of my function. We were graphing a quadratic. So we want to lower our cost, right? So we're going to want to see which X value minimizes our cost. Because at some point in time, and I think about this because my husband works at Kubota. So at some point in time, it's no longer cost effective for them to continue to produce a tractor. First of all, cost of labor. If you produce too many, you've got people putting in overtime hours, and that costs you money. You've got to increase your staffing, which costs you money, benefits and all that stuff. Then, if you've got it sitting somewhere, you got to pay for it to be in some sort of storage. So there's a lot of factors that come into that, but at some point in time, we're going to start increasing. Our cost is going to exceed our benefits. So we're wanting to minimize the cost. Let's see how many computers that we would want to produce to minimize our cost. Now, if you look at this equation looks pretty ugly, doesn't it? But if we've got the tool of the graphing calculator, we can actually find our minimum value. You can start hitting trace. If you hit the trace button, see how it's there in white, so all I got to do, and I can just scroll along and let it go find what I think is the minimum, right? Somewhere around in there. Looks like it's around 1,200 minimum. And what would be the optimum number of computers? Probably around 40. So let's go and calculate the minimum. So second calculate, go calculate the minimum. You guys should be a little bit familiar with, because we did this, sort of did this last time. Do you see how it's going to ask us the left bound and the right bound? So we're going to need to scroll a little to the left of where we think that minimum is, and then a little to the right. So I'm going to go through the minimum and hit enter. So I'm saying, hey, I think my minimum's somewhere between here and here and here. Would you guess it for me, calculator, and do my calculations for me? And it does. And it says the minimum value or the minimum cost is going to occur when we produce 41 computers. So we can do a cost analysis to figure out what would be the maximum number of computers we'd want to produce in a day to keep our costs at a minimum. Right? Computers in a day. More than likely, that's all that your line can handle to shove out before you have to go over to overtime, and then you're paying people, you're paying all 100 employees overtime, and then your cost starts to go up. So around 41 computers would be an optimal value for our costs. So that's just playing around with the calculator and seeing its functionality. And this just gives you a way to kind of look at it. They do show the table, so I'd like for us to kind of look at the table. Do you see how the table's in yellow? So I'm going to hit second graph, and it gives me my table of values. Why at 0 do I get an error? Because right here, you can't have an x value that's 0. So that would be, your domain would be limited somewhere between 0 and it says 80 would be your maximum. But if I only produced one computer, my cost would be $21,000. So not very cost effective. But as I scroll down, I'm trying to minimize my cost. See how I'm 2,000, 1,600, 1,500, 1,400, 38. 39, 40, 41. 41 is my minimum number of computers. You can't produce a portion of a computer, so we'll just go with 41 as being our most optimal production number. So, anywho, gives you a little idea of what your calculator can do for you when factoring and all our nice little hands-on stuff doesn't work. We can use the tool, but we've got to be able to interpret. So I kind of have always said the calculator is only as smart as the user. You know, trigonometry is used for folks who do land surveying. And yes, their computer will do a whole lot for them, but they've got to be able to interpret those results and understand where those calculations come from. And they also need to be able to spot errors, you know, with what might be a problem. All right, so we're going to carry on, and now we're going to talk about what David brought up earlier, was whether we have even functions or odd functions. A function is an even function for every number x in its domain if the number negative x is also in the domain. When we're looking at an even function, my favorite even function that we use most often is a parabola. Right? This is your basic y is equal to x squared. Or, if I write it in function notation, f of x is equal to x squared. Most basic, this is your parent function, because I haven't moved it anywhere. But the case is, if I were to replace my x with a negative x squared would still give me back x squared, right? Because that negative gets moved away or gets absorbed in. So this would be an even function. That's your basic one. Now, I think I remember something else looking something like this. Y'all remember when you substitute a negative x in? What was that? Symmetry about the what? The what? You were right. Okay, but it's actually going to be the y-axis, because if I were to graph this one, it goes through the origin and it is symmetric about the y-axis. So an even function is going to be symmetric about the y-axis. All right, if a function is odd, every number x in its domain, the number negative x is also in the domain. So the most basic odd function that I know how to graph is a cubic function, where if this was your axes, it's going to go through the origin 0, 0, and it's going to appear to look like that. what it says is if I substitute a negative x in and I run it through negative x cubed, what is negative x times negative x times negative x? It's going to be a negative x to the third power. So it comes outside that, and I can actually say it's negative 1 times x cubed, right? So it represents this in that it would be the negative of what we started with. The negative of what we started with. So this one is an odd function. Odd functions are symmetric about the origin. Good. Odd functions are symmetric about the origin. A function is even if and only if its graph is symmetric with respect to the y-axis, and I showed you an example. So your basic example to kind of help you, remember I'm not good at memorizing facts, but I am kind of good at relating it back logically. My most basic even function is a y is equal to x squared. So it reminds me that, hey, it is symmetric about the y-axis. My most basic that I can think of that is an odd function is x to the third power. Now I haven't added or subtracted anything. You start adding and subtracting stuff and it can change it. So it has to be the most basic, and I know its graph kind of looks like this, goes through the origin, and I could rotate it about the origin and get symmetry. So why do we not have something that is symmetric with respect to the x-axis? If something is symmetric with respect to the x-axis, what happens? It's not a function, right? So it would not be a function. So both of these are defined as a function is even or odd. Well, it cannot be a function if it's symmetric about the x-axis, because then it would fail that vertical line test. So, all right. So, determine whether each is even, odd, or neither. So the first one, even. Second one, it's neither. Because if it's symmetric about the origin, it's got to go at least through the origin so you could spin it around the origin. I'm sorry? It should or be symmetric about the origin that you can see that it reflects. This one is symmetric about this particular point. If I were to spin it around this point, I would see that it would reflect back on itself. But it doesn't ask me for symmetry about 2. It asks me if it's symmetric about the origin. So this one is not. This one. Yeah, yep. That's why I said you got to really know and test that. So this one is neither. And this one, of course, goes through the origin. And if you can imagine taking it and spinning it, can you see that this one, if you spun that about the origin, would reflect back on this picture here? Okay. All right, so from an equation, we should be able to identify if it's even or odd or neither. So let's review. If it is even, then this happens. If it is odd, then this happens. Okay, so I've got to test this to see if it's even or odd. So my first test for A would be that I'm going to take my original function and replace everything with a negative x and simplify it down. Now you can't just look at this and see, you've got to show and be able to prove for the test. So if I ask you, is it even or odd, I'm going to expect to be able to see work, not just a word. Okay? So I'm going ahead and giving you heads up, don't just guess, even, odd. I want you to actually show me by giving me the work. So negative x cubed plus 5 times negative x. Now we already know that negative x cubed becomes negative x cubed. And then positive 5 times a negative x gives me a negative 5. And then, can I factor out a negative? Aren't these both negatives? Factor out a negative and I'll get x cubed plus 5. So if you notice this, that is what your original function was. And all it is multiplied by that negative. So this one is an odd function. I'll let you test the other two for even or odd. Continue. Increasing, decreasing, or constant. This is like the slope dude. Positive slope, negative slope, zero slope. So we're going to talk about whether a graph is increasing over your x values, decreasing over your x values, or constant over your x values. So, where is the function increasing? This is just me showing a picture. This function increases where I have drawn it to be red. Agreed? But if I were to define its interval of increase, I base it on the x values. So I look at the graph. The graph is the production of the output. It is the y values that's showing me that it's increasing. But when I say where is the function increasing, it is increasing for any x value between -4 to 0. So between these two values of x, from -4 to 0, my graph is increasing. From 0 to 3, my graph is constant. From 3 to 6, notice I'm choosing the x values because it's the y values that decrease here, but it's over what x values is it decreasing. So the biggest thing that I used to have trouble with is I would always put, or students still do, they'll put the y values in that show me that they're increasing because the y values are from -2 to 4. So you want -2 to 4, right? No. I want to know over what input values does my graph increase. Where is the function decreasing? -6 to -4 and 3 to 6. Now, if you notice the answers, if I can actually get it to pull down, there's no equal to's on these. Because at the beginning point and at the ending point of where something changes directions, right here, at this -4, right here, my graph is neither increasing nor decreasing. It's at a relative minimum. So it's neither increasing or decreasing, so we don't include those points with brackets. So intervals of increase, decreasing, or constant will never have anything other than ordered pairs, parentheses, not brackets, because you're not going to include those endpoints as being increasing or decreasing. So constant from 0 to 3. 0 to 3, this is in inequality notation or algebraic notation. This is in interval notation. I prefer this because I understand that these are not two ordered pairs.
I was about to say, I really don't do that.
I'm very comfortable with either. I speak both. But I know that students sometimes make this into thinking as an ordered pair and get confused. So I don't care. Whichever you're comfortable with and can clearly mathematically explain to me, that's fine. So I don't need all these definitions. We're good. All right, so local max and local min. Local maxima and local minima. It's where is it maximum, where is it minimum, and we're talking about local, we're talking about looking in between specific intervals of values. So if I were looking at a graph, notice that I have endpoints here. So if I'm asking you to find the local max, I'm going to give you boundaries to go look for that maximum value. We're going to find where does it top out. Notice it says on the left-hand side is the increasing side, the right-hand side is the decreasing side, so the maximum is going to occur at that highest point, kind of like a no-duh moment, right? A minimum, or a minima, is going to occur at the minimum point, but I'm going to give you a boundary between some value of x on the left and some value on the right. There's no endpoints. There's no arrows here. So that's part of the reason that you'll have localized maximum and minimum values. All right. So it asks you to find the local maxima and local minima from the graph of the function and determine where the function is increasing, decreasing, or constant. So do you notice it has endpoints, or it has arrows at the ends? So we're going to be looking between some boundary values for minimum. So we're looking at the absolute minimum would be located right here. But if we're looking at small intervals, we got a minimum that occurs here, and we've also got a minimum that occurs here. And you've got one maximum. So it says, at what number, if any, does f have a local maximum? So at the number, and David said, x of 1. There is a local maximum that occurs when the x value is 1. Now that 1 is not the maximum value or the local maximum value that occurs. The value of the local maximum is the y value, but it occurred at the x value of 2. So at what number does it have a local maximum? At 1. But when it asks you what is the maximum in that localized area, it's going to be, hello, go away. It's going to be the y value of 2. So if I were graphing this for you, these endpoints, if I were asking you for the absolute maximum, there is none. Arrows pointing out up, right? But if I'm saying give me the local maximum, I'm talking about in between some restricted values. Where does it have the highest point? All right, and then you can see these two red values give you your local minima. They're localized in that I can put a boundary on the left and the right-hand side and say, hey, a minimum occurs there, and then a minimum occurs again over there. So you've got some particular values. Undo, that didn't work. So you've got a local minimum occurring at x equal to -1 and x equal to -3, and those local min values are 1 and 0. 1 being the y value, 0 being the y value. Those maxima and minima cause you to be able to start and stop your intervals of increase and decrease. Now, for my college algebra students, I would tell them, ignore the arrows and walk it like you're going hiking or skiing or roller skating, right? This purple is a interval of decrease, right? Interval of decrease.
You're always going to read left and left.
You're always just like a book, reading left to right. So you're starting with your dude on the left-hand side, and he's going to go on this half pipe, whatever this is, right? So notice that my interval of decrease is defined from x values -infinity up to the x value of -1. That's the problem. The definition of an interval of decrease or increase, folks cannot wrap their brain around the fact that I am decreasing in y over the x values of -infinity to -1. So instead they'll tell me from +infinity to +1 I'm decreasing. That's not what I'm wanting. I'm wanting over what input values do my y values decrease. I've already identified that my y values decrease, so now tell me over what x values. Okay, so I'm not going to kill this, but there's your intervals of increase and decrease. Notice that there's parentheses around everything, no brackets, because at your local max, at your local min, they're neither increasing nor decreasing. All right. Sometimes I'm a little surprised by what I continue to do with this because I kind of pulled this in from the Pearson products because I got dumped this. So I got to look over it and I was like, yeah, these look good. I can toss that out. So finding the absolute maximum and absolute minimum, if they exist, well, over this particular graph, we do have the absolute highest spot and we do have the absolute lowest spot. Notice that 4, 4 is not an absolute minimum, right? It is a local min, but it is not an absolute min. So when you're asked for absolute maxes or min, go to the highest, that's your absolute maximum, and go to your lowest, that's your absolute minimum. Now what would cause this to be a problem is if I added an arrow. If I added an arrow, what would I change my absolute maximum to? Okay, but positive infinity is not a number, so the absolute maximum, it has none. Because we can't touch it, taste it, feel it, smell it, it's not tangible, we would say there is no absolute maximum if I added that arrow there. No, just say none. Just say if you want to, you can overkill it. It goes to positive infinity, therefore there is no defined absolute maximum. I mean, that's if you're wanting to overkill. But NONE means the same thing to me. There is none. All right, so absolute maximum, absolute minimum. Now people are tempted to say that the minimum is when x is 3, the y value is 1, but why would there be no absolute minimum for this particular graph? What is it? It's an open circle. There's a hole there. So it approaches this value from both sides, but it doesn't actually touch it. So at that particular point, there's a hole. And so there is no absolute maximum or minimum because I can keep getting really close to 1, but never actually touch it. So there's not an identifiable value that is my absolute minimum. My absolute maximum occurs at x when y is 3. Does that make sense with that hole being there? Okay. All right. Finding the absolute minimum and absolute maximum on a graph. Find the absolute maximum and the absolute minimum. Now the absolute maximum occurs when x is 5, my y value is 4. But what happens here? Because it's a constant over a particular interval. What do we do for that? We'd have to define it as that interval. The absolute minimum occurs over the interval from 1 to 2. So the absolute minimum is identified as a y value of 1, but it occurs on the interval from 1 to 2. So just a more explicit or explaining that definition. This one has a what? Minimum, but an arrow. So a minimum occurs, but what do we say about the maximum? There is none. There is no absolute maximum because that arrow goes off to infinity and beyond. All right, so I think you guys get the point, right? Extreme values. All right, so use a graphing utility, and it tells us to graph between the x values of -2 to 2, and let's approximate where there is a local max or a local min. Now, with it telling you between -2 and 2, that helps you to define your window values, right? So if I'm going to put that into my calculator, which where did my rabbit go? All right, so you guys put that in while I try to find my calculator again. It just sometimes just disappears. Two x raised to the 3rd power minus 3x plus 1. I'm going to change my window so that it is restricted between -2 and +2 on my x values. And I'm going to graph it. So I'm looking for local maxes and local mins, which means that I'm not going to be looking here and here, right? Because it says not equal to on those x values. So we're not looking for these two values. We're looking for the highest point here and the lowest point here for my local maxes and my local mins. So under the calculate function, you should be able to do so. So second calculate, I'm going to look for a maximum that occurs. My cursor is blinking, so I'm going to go back this way. And because it kind of flattens out right here, I'm not quite sure, so I'm going to make sure that I go wide enough on my boundaries for it to be able to calculate. So do you see where my arrows are? Boom, boom. And I'm wanting it to find my local maximum. And I ask it to calculate it. And it occurs at negative 0.7071078 with a y value of 2.4. How's that Wabbit app working? Did you find a different app, or is that the Wabbit app? Is it?
Yeah, it works out fine. 2.4.
Good.
This is
0. Yeah, that negative 0.07. And Jacob, you've got the app as well. Why yours looks different than his? Oh, okay. So you just use the screen itself, right? And does it work is it fairly easy to work within? Show me how you put in your function y is equal to. Okay, so right now you've got a couple of things on here.
Yeah, that's.
But it allows you to change those colors. That's cool. I like that. All right. So do y'all understand how to use your calculators to go find that maximum and minimum? Okay. All right, Caleb, is everything okay? You got a question for me? Anything we can look at? Okay. It looks like everybody's kind of got one. Have you got one, or do you want to? Excellent, excellent. I just think that I think it'll be good for us to use it. And I know Mr. Schrader said this semester he was really going to be pushing the calculators a whole lot more. So I'm glad that if you guys can use them, I think it'll help us to kind of expand on it a little bit. So you guys could also go after your local min, the same process, and that's just going to take some practicing going through. But using those values, it's going to ask me where is f of x increasing and where is it decreasing. So let's go, and I want y'all to go and define for me. I know that we had a local max that was at 707, and help me out, Mickey, was it 2.4? Okay, so that was our local max. And then somebody go find our local min for us. I'll let y'all do that. Okay, so it was 0.707 again. And then what was it? Negative 4.1. Excellent. Oh, sorry. You probably said that. I just can't hear very well. All right. So if I go back and look at my graph, can I now define where it is increasing and where it is decreasing? I wished it would let me draw on top of it, but for some reason it's not letting me. Let's see. So, it's not. So from here to here, it's doing what? Increasing. And from here to here, it's doing what? Decreasing. And from here to here, it's increasing. So I should be able to, from looking at that, I've got increasing from left to right. So what values would I write? I'm going to write increasing here. And I'm going to say, what's my lowest x value on the left-hand side bounded by that? That's going to be my negative 2, right? X value. And then I'm going to go up and increase to this local max of negative 0.7. And I'm shorthanded and being lazy about it. But from negative 2 to 0.7, I'm increasing. And then let's go ahead and finish it. It's also increasing from this value to positive 2, correct? So I'm going to union it with negative or 0.7 to positive 2. Those are our intervals of increasing. My decreasing is going to have to occur in between those other two x values that I skipped over. So from negative 0.7 to positive 0.7, my graph was decreasing. From the x value of negative 0.7 to the x value of positive 0.7, my graph was decreasing. All right, guess what time it is? Doesn't it just fly by? I love math. It just flies by. I know, I'm a nerd like that. All right, so what is your homework?